So assignment. Let me start. Did I start that? I did. Yeah. Assignment 4 is due Friday, the 26th this week. And exam 2 will cover chapters 4 and 5. We should be starting chapter 5 today. And the final exam is going to cover chapters 6 and 7. So here's the 4th assignment. Any questions? Any help getting started on that? Oh, I had some typos to fix here, didn't I? Not fix those typos. Questions on any of that? The typo just like it should say always here as well. These should be worded the same. Although the word always there is just kind of superfluous. Anything? Questions? And like last time, if you write something down and you're kind of like not sure if it's sufficient or correct or something, you can always send me an email, and I will, take a look at it for you. Okay. So in lieu of, actually being able to sit down and work together, we can do that. If you want to sit down and work together, we can do it on Collaborate Ultra, or I can help you with your writing. As long as you've got a working webcam, we can do that. Okay. All right. So let's go back to chapter 4. So we've covered everything for the assignment on chapter 4. We're just on some few extra things that actually we'll talk about later in the course. So last time I was telling you about the type of statement where you say something like the following are equivalent. So when someone states the following are equivalent, and then they list out, 3, 4, 5 things, it means that either all of them are true, or none of them, or all of them are false. All true or all false. In other words, A is logically equivalent to B, A is logically equivalent to C, A is logically equivalent to D, B logically equivalent to C, and so on and so forth. And how do you prove that in a more minimal fashion? So rather than for 4 items that you're saying are logically equivalent, each logical equivalence is 2 implications. So there's 6 logical equivalents among 4 items, because there's 6 pairs among 4 items, which would be 8 implications. But you don't have to show 8 implications. Basically, you have to show enough implications to create an arrow diagram with a path between any 2 points. Okay? Because you can use this tautology called hypothetical syllogism, which says, when you have A implies B and B implies C, then you get A implies C for free. So arrow from A to B and arrow from B to C gives you arrow from A to C automatically. So to prove all 8 of these all 12 of these arrows, this is enough. Because I can get from any one point to the other in both directions. I can go from A to D this way and D from A that way. A to C this way and C to A that way. Or some other, like instead of A, B, C, D, A, you can have A, C, B, D, A. Or something like this. This has 4 arrows. This one actually has actually has 5, but it's less than 12. A implies C, C implies B, B implies A, and then B implies D, and D implies B. So that's another such diagram. It's got more arrows than these two. The smallest number of arrows is always going to be a cycle like this. Not that you can always do a cycle. Sometimes it's more convenient to do things with a few more arrows, but this is the standard. So, for example, so F is a bijection when it is both injective and surjective. Remember, injective means one-to-one, surjective means onto. All right, in other words, is one-to-one. In other words, is onto. So, given a function f from a domain to a range, where D and domain and range are finite sets, the following are equivalent. So f is both injective and surjective. That's what bijection is. F is an injection and a surjection. 2, f is just an injection. 3, f is just a surjection. So with finite sets, you can't have one without the other. An assumption where D and R are finite sets with, the order of D equal to the order of R. It's not quite true yet. Are finite sets with the order of D equal to the order of R. Or the order of, I guess you could say, no, it has to be order of D equal to order of R. And of course, this is not true with infinite sets. Right, so for example, if you have f from the natural numbers to the natural numbers defined by f of x equal to 2x, right? So, f of 0 is 0, f of 1 is 2, f of 3 is 4, 3 is 6, f of 1 is 2, f of 2 is 4, f of 3 is 6, f of 4 is 8, so on and so forth. That function is injective, but not surjective. Right? That function is one-to-one, assuming that f of x is equal to f of y. Right, here's the proof of that. Assuming fx equals fy, right, we get, right, well, f of x is 2x, is equal to 2y, but then you can just cancel those, so you have x is equal to y, as required. Right, but it's not surjective right? Because f of x is not equal to 3. So 3 is a natural number, but f of x is not equal to 3 for any x in the natural numbers. Natural numbers was the non-negative integers, 0, 1, 2, 3. Right, or if you did something like this, f from the natural numbers to the natural numbers defined by f of x is equal to x over 2 when x is even, right? Let's write it like how they do in calculus. Piecewise function. X over 2 when x is even, and f of x is just equal to x when x is odd. Right? This is surjective, but not injective. Right? Surjective, if x in n is odd, then f of x is equal to x. If x in n is even, then f of 2x is equal to x. So no matter what x it is that you're looking for in the range, which is the natural same as the domain, no matter what number it is you're looking for, you have something in the domain that goes to that range element. When x is an even number, f of 2x goes to x. Because when you divide 2x by 2, you get x. If x was odd, well, f of x was equal to x when x was odd. Not injective. Give me two numbers whose images are even. Right, f of what is equal to f of what for different numbers. What's f of 6? According to this definition here. What's f of 6?
3.
3. What else is equal to f of what else is equal to 3?
F of 3.
Yeah. F of 6 is equal to f of 3, which is 3. But 6, of course, is not equal to 3. So it's not injective. Surjective, but not injective. So for finite sets of the same size, these things are equivalent. Okay. And then if they're not the same size, if the size of the domain is not equal to the size of the range, then this fails as well. Right. So you had a domain with 3 elements and a range with 4 elements, 5 elements, or whatever. Something that looks like this, well, that's injective, but not surjective. If you had a domain that was larger than the range, oops. So this is surjective, but not injective. Okay, so just a word of caution about that statement there. Surjective and injective mean the same thing when the domain and the range have the same size and are finite. But same size and infinite, no. All right, proof. Okay, so we're going to prove that 1 implies 2, 2 implies 3. Right, so we'll prove that 1 implies 2, 2 implies 3, and then 3 implies 1. And then automatically you get that 1 implies 3, because 1 implies 2 and 2 implies 3, therefore 1 implies 3 by syllogism. 3 implies 2, because 3 implies 1 implies 2. And 2 implies 1, because 2 implies 3 implies 1, right? So you only have to prove the 3 implications there to get all 6 implications that you want. So 1 implies 2. So you usually write it like this. So assume F is a bijection. Okay, we want to show that F is an injection. What does it mean to be a bijection? What does it mean to be a bijection?
F is both injective and surjective.
Right. So we have to show that it's injective. So what do we write? Right, we're assuming that F is a bijection. Now we have to show that F is an injection. But the definition of bijection is that it is an injection and a surjection. Therefore, F is an injection. For what reason?
By definition of bijection.
By definition. Well, what you said is better. By the definition of injection. All right. 2 implies 3. Right? Assume that F is an injection. Okay, we want to show that F is a surjection. Okay, let's label the elements of D. So D is a finite set. As 1, 2, 3. I mean, whatever those elements are, relabel them as 1 to n. All right, because F is an injection, F of 1, F of 2, F of 3, F of n are all what? Actually, let me use a different notation. Instead of just 1 to n, we'll say D1, D2, Dn.
Equal to one another?
Not equal.
They're each unique.
They're distinct is the preferred term in this case. But yeah. are how many distinct elements of the range. How many distinct elements? Right, there's n domain elements, and then when you hit them all by f, they turn into range elements. How many range elements? Since they're distinct. The obvious answer. Sometimes you have to state the obvious. Or it helps to state the obvious if it can be said, very clearly. Distinct means they're all different. Okay? How many things are there here?
N.
N. So how many things are there here?
N.
All distinct. How many?
N.
N. Are n distinct elements of R? Okay, since n is equal to the number of things in the domain, and the domain and the range have the same size, it must be the case that R is actually equal to what? So if I have a list of names for the class, and I go down that list of names, like taking roll call, right? Adams here, Barber here, right? Starts with C. Cedric here, right? So on and so forth. And if everybody says here, that means what? The number of names I read is the number of
The number of
class.
names you read.
What's that?
The number of names you read.
The number of people in class is the same as the number of names I read.
Yeah.
Yeah, that I said it wrong. My apologies. That means the number of people that are in class that day is the number of names that I read, which is everybody on the class list. Okay. So there's n people in the domain. How many are accounted for here? There's n people in the range. How many are accounted for here?
N.
N. So the range is
N.
no, n is a number. The range is n elements, and what are those n elements? The range has n elements. We've accounted for all of them here. So the range is those elements. F of D1, F of Dn. Which means that what? F F is what?
Surjective.
Surjective. There's n elements in the range. Here they are. So the range is that. Okay, and everything in the range is f of something in the domain. That by definition is surjective. All right, 3 implies 1. So, and 3 implies 1, let's go back to that list. All right, we want to assume f is surjective, show that f is bijective. So, assume that f is surjective. All right, in order to show that f is bijective, we need only show that what? Not only, I guess, but we need to show that f is what?
Also injective.
Is injective, right? Right. Well, because f is surjective. Well, so let's write the elements of the range, or label the elements of the range as as R1, R2, all the way up to Rn. Okay, because f is surjective, right, because f is surjective, right, for each Ri, there is what? What does surjective mean? For everything in the range, there is something.
In the domain.
There's something in the domain. What do you like to call it?
D sub
I.
I.
Yeah, so match indices. There is di in the domain such that what? Such that f
Of D sub I
uh-huh,
equals R sub I?
yeah,
Oh.
yeah. That's the definition of surjective. Okay, well, all right, the elements R1 to Rn are distinct, and so D1 to Dn must also be n distinct elements of D where the order of D is equal to the order of R is equal to n. Right? I mean, we've got the range elements right here. Because f is surjective, there's something in the domain that goes to everything in the range. But these things in the range are all different, so you can't take the same element in the domain and send it to two things in the range. It's just not what functions do. Functions take one thing in the domain, send it to one thing in the range. You know, the special thing is when everything in the domain comes from one thing in the range. But that's what have to happen here. These guys are distinct, therefore these guys are distinct elements of the domain. But the domain only has n things in it. Um, I think I'm going off on the wrong. We're trying to show that it is injective. Right. Therefore, okay, the domain is equal to D1 to Dn, and no two elements of the domain, no two elements of D are assigned to the same element of R, which means that F is injective. Right? Because F was surjective, right, we have these elements D1 to Dn in the domain, where f of D1 is R1, f of D2 is R2, f of D3 is R3, so on and so forth. But there's only n elements in the domain, so that's got to be the whole thing. That's got to be the whole domain right there. So since all those elements in the domain went to different things in their range, there's nothing else in the domain that goes to those same things in the range, which means you're injective. Unfortunately, this proof, I mean, okay, so we did what we needed to do. We showed 1 implies 2, 2 implies 3, 3 implies 1. Unfortunately, the best proof of this statement is no proof at all, because it's just painfully obvious once you think about it and understand what's being said. So sometimes in math you have to do that. You know, you just have to kind of state the obvious and wait for everybody to, you know, to just sort of say, oh, right, yeah, that's obvious. But, you know, just as a matter of illustration, we did an actual proof. And sometimes it's maybe a little hard to prove the obvious. I mean, because you have to set up all the notation. So it's not the best example in the world, but, you know, it's something that needed to be done. Not the best example in the world of the following our equivalent, but it's the first one we've done. All right. So, by the way, when I'm not really going to talk about this, but okay, a function f from domain to range has an inverse function if and only if f is a bijection. Bijection. Okay, when f is a bijection, then we define the inverse function from the range to the domain by f of y is equal to x, f inverse of y is equal to x when f of x is equal to y. Okay, but that only makes sense if the function f is a bijection to begin with, because you say f inverse of y is equal to x, well, you can only cover y. You can only say f of y is equal to x when f of x equals y, when there is something in the domain that goes to that thing in the range. So that means you must be surjective. But if there was two things in the domain that went to the same thing in the range, right? So like if you had two things in the domain, D1, well, A and B in the domain, both go to y in the range, well, then what's f of y? F inverse of y. What's it going to be? Is it going to be A or is it going to be B? I mean, given a specific function, you could say, okay, we'll pick this one. Okay, but it's not really an inverse function. I don't really want to talk about the inverse function any more than that. Okay, so a function has an inverse function if and only if f is a bijection. And in that case, when you do have a bijection, then you define the inverse function by f inverse of y is equal to x when f of x is equal to y. But that definition only makes sense when you have a bijection. If you don't have a bijection, it doesn't make sense. Right, I mean, like, what is the, if f of x is equal to x squared, then what is f inverse of x? What's it going to be? What should it be? When you're going from, the set of real numbers to the set of real numbers. Well, even if you're going from the set of real numbers to 0 to plus infinity. Okay, it's a surjection, but it's not an injection. What should be the inverse function of f of x equal to x squared? Well, you would say to me, oh, it should be square root x. Why? I mean, why should f of 4 be equal to 2? Why shouldn't it be negative 2? In order to make, sense in calculus, we would say the inverse function is the square root of x. But that's only if your domain is the set of non-negatives. So, for example, f from 0 to plus infinity to 0 to plus infinity defined by f of x equal to x squared is a bijection. Why is that? Why is that a bijection? Right, a function, if you look at the graph of a function, of a calculus function, well, I mean, like a curve in the plane, it's a function when it passes the vertical line test. And every vertical line intersects once. It's 1-to-1 when it passes the horizontal line test. Every horizontal line hits it only once. So 1-to-1 and onto. So f of x equal to x squared is a bijection because it's 1-to-1 and it's onto. It passes the horizontal line test. Every horizontal line intersects it exactly once, over this range here, 0 to plus infinity. So f defined by fx equal to x squared is a bijection. So it makes sense to say that f inverse of x is equal to square root x defines the inverse function inverse from 0 to plus infinity to 0 to plus infinity. However, if f from R to 0 to plus infinity is defined by f of x equal to x squared, then there is no well-defined way to choose f inverse of x, right? Square root of x or the negative square root of x. All right. Not no well-defined. There's no universal, not well-defined or universal way to choose it. All right. The final topic in this section, which isn't on the fourth assignment, but we will talk about it in the last chapter on metric spaces, composition of functions. So let's talk about it here. All right, let's start the discussion of it here. Given a function, well, given functions, sorry, f from A to B and g from B to C, right, we define the composition g following f from A to C by gf of x is equal to g of f of x for each x in A. So here's A, here's B, here's C. Essentially, you're taking x in A, and f takes it to some guy y in B, and then g takes y to some guy z in C. And f of g just, skips over the middle part. Or sorry, g of f. G following f, sorry. G following f, or gf, goes from x to z straight away. Okay, so usually we say gf as g following f. Has anyone ever seen g following f written like this?
No, I haven't seen it quite like that before.
Oh, I'm sorry, like this. I mean, this little circle thing.
Oh yeah,
That's not standard. That's totally not standard. That's the way they do it in, like, kind of in high school texts for some reason. But it's just not necessary. I mean, it's not just not necessary. It's non-standard. Okay, people just write it like that. Just G and write it like multiplication. It's not multiplication. It's composition. Okay, but they just write it like multiplication. There's a good reason for that. I mean, it's just more streamlined. That's the best reason, but there's other reasons besides that. So, for example, I mean, take this kind of bubble diagram here. And let's just write out some stuff, some elements here. So we'll put 3 elements here. 1, 2, 3. Put a couple things here. Little a, little b, and a few things here. W, X, Y, Z. So we'll say f of 1 goes to A, f of 2 goes to A, f of 3 goes to B, and then f of, or let's make a C, yeah, that's fine. Yeah, that's fine like that. So this is F, this is G. So GF of 1 is equal to, well, you write f of G of 1. What's G, or G of f of 1? G of f of 1. Right, well, what's f of 1? F of 1 is A. Right, and then G of A is W. GF2 is equal to G of f of 2. Right, what's f of 2 is equal to A. F of 2 is A, and G of A is W. And then G of f of 3 is G of, or G following f of 3 is G of f of 3. F of 3 is B, so this is G of B, and then G of B is X. Alright, so G following f of 1 is W, G following f of 2 is W, and G following f of 3 is X. Okay, so this note, it's important to get the notation right. I mean, you may be thinking to yourself, well, you know, this is, you know, really quite simple. It is. You know, this example is very simple. But it's very important to get the notation right. Okay, this is the preferred notation for writing down composition. Just, you know, G following F, and you just write them next to each other like that. What is the meaning of GF? G following F. The meaning of G following F is that G following F at argument X is G of argument F of argument X. Okay, that's the definition of G following F of X. Got to get the notation right. It's really important. So this example is also, you know, notational, not just conceptual. So anyway, once you see these things here, you can draw the function just by itself without the sort of intermediate b, like so. So what was it G following F was W for the first two, and then Y for the X for the second. So this is G following F. All right. Now, this is, of course, the same definition of composition when you restrict your attention to just functions from the real numbers to the real numbers. Okay. Given functions f from the reals to the reals and g from the reals to the reals, defined using elementary functions, say, this is, this more general definition specializes to the one you know from calculus. From calculus and pre-calculus. So, for example, if we had that f of x is equal to, and it's not defined over the whole reals, of course. You're going to be missing x equal to -2, but 3x plus 1 over x plus 2. So, I mean, leave out -2 or something like that. And g of x equal to, what shall we say, x squared, right? So given f of x defined this way and g of x defined that way, g following f of x is defined as g of f of x, right? So that's g of this thing, 3x plus 1 over x plus 2, which is that whole thing squared, right? F following g of x, right, is f of g of x. What is g of x? G of x is x squared. So that's f of x squared. And f of x squared is 3x squared plus 1 over x squared plus 2. And of course, this is not the same thing. This is 9x squared plus 6x plus 1 over x squared plus 4x plus 4, right? So those are not the same thing. And of course, you can also do g composed with g, right? So g squared, right? This is defined as g following g of x. So that's g of x, right? That's g of x squared. But g of x squared is x squared squared, which is x to the 4th. All right, so that would be g following g, which is usually written as g squared. Similarly, g to the 3rd is going to be x to the 6th, etc., etc. All right, so you can do g composed with f composed with g, g composed with itself, f composed with itself, so on and so forth. All right.
Isn't the chain rule a composition of functions?
It's about compositions of functions, yeah. Of course, we're not talking about derivatives here, right? Just compositions, just by itself. But yeah, of course, the chain rule is about composition of functions. All right. So there's a couple things I wanted to say about it, besides what we have said. But we'll cover that next time. So that's all the time we have for today.